All right, so let's quickly review and pick up where we left off. So we're currently doing a linear regression model. And what we're doing, this is going to be a supervised data model. What does that mean if we say supervised data model?
We're going to input the information ourselves.
Yeah, well, we're going to create a model first, and then we're going to take that model, and then we're going to apply that to some test data. So while 6% of households are pregnant at any given time, if you look at our test data, we have 50-50. So you could potentially create this situation of overfitting, but this model takes care of it and is not suspect to overfitting. So what we did is we basically went in and we took these, we have all these different features right here. So whether, person's male or female, pregnancy tests and other items. And then we put in this linear combination. What this was doing is it's basically taking all those coefficients times the sum product of each row. If we look at this formula, we have B2 to U2, so it's always going to take those guys, and it's going to take each row by row as we go from B8 to U8 and fill down. So it's always multiplying this top row, row 2, by each row down here for each one of these linear combinations. And once it takes that, it comes up with this squared error. Okay, so we take that squared error, and then we summed up all these squared errors. And then after we had all the sum of squared errors, then we put that into solver. So we put that into solver to go drive down and find the minimum value in here. But what was our squared error formula? What did we do? Anybody remember? So we have what? We have the pregnancy minus that linear combination of basically taking that coefficient on the B row times each applicable row. So it's like row 2 times row 8. And then it was like on the next one, it was row 2 times row 9. Then the next one, row 2 times 10, and on down the line until we got through all 1,000. Once we had that, then we subtracted pregnancy, whether a person's pregnant or not, so 1 or 0, minus that linear combination, and then we squared it. The second we squared it, what happened to our solver problem? Could we use our first go-to formula when we're doing our solver is always what? So if you had a choice of like the different models that you're going to use for solver, which one would you guys want to use? Which one's faster, most accurate, most consistent? The linear, right? Good. Awesome, guys. Awesome. So the linear is most consistent and fastest, but however, comma, what is this formula here in the X column? We did a subtraction. That's okay in the linear formula, but then we did what? What's that caret 2? So we squared it. So the second we have a square in there, we have a quadratic. So now it's no longer a linear line. Therefore, we had to use what method now? We used evolutionary. Good, good. All right. So then we used evolutionary, and then what happened, and again, this is just like mind-boggling, is that it takes the sum of the product. So it takes the coefficient in the 2 row times like 8, and some products that up, and then it takes the row 2 times 9, and then row 2 times 10, and on down, and it basically works all that down to get the sum product to where you put the coefficients up there at the top, such that it minimizes that squared error formula. So if you think about all the math this thing is doing, it's taking each one of those, summing the product, taking a squared error, adding it up, and then for each one it's selecting a value such that that's minimized, which is pretty insane. Because this was evolutionary, all of our solutions are a little bit, could be different up here for our coefficients. And then we did conditional formatting, and anything that has darker colors means those are things that are most susceptible for someone that's pregnant. So if we look at this, what did you guys have? So I have like pregnancy test, folic acid, prenatal vitamins, prenatal yoga, are kind of like things that if a person is buying that or doing these things, they're probably going to be pregnant. So what did you have, Brian?
The pregnancy test.
Okay.
I had folic acid too, prenatal vitamins, yoga, ginger ale.
Okay. So yeah. So okay. So the deeper the green means is more. George or Ryan or Alex, did you guys have anything different or about the same? Barely. Okay. So Ryan and Alex, did you guys have anything different?
Looks the same.
Looks pretty same. Okay. Yeah. So these are kind of like the big things. So one of the things so if we kind of eyeball this, if we look at this, so now if we come over here and look at the column, the higher the number is over here, the more likely they're pregnant. So if you look at, like let's go down here, look at like 1.41. This guy is like really big here. What did this person buy? They bought maternity clothes, they stopped buying wine, they stopped buying ciggies, they have C-bands for nausea, they bought prenatal vitamins, didn't buy folic acid though, didn't do birth control, maybe should have did that if they weren't trying. So if you look at this, these are kind of like things that drove this one, okay? So if we look, if we kind of eyeball this, this looks pretty good, but what we're going to do now is we're going to separate out each one of these, and we're going to say, what's the probability that this is a good model? What's the probability this just happened by chance? And what are the key coefficients that drove this? So that's what we're going to be doing over the next couple of days here, okay? So you have your thing up, George? Yeah. Perfect. Okay, cool. All right, so let's go on into slide number 13. So one of the things we could have used was this lin estimate function to do linear regression, but that would be no fun. That would be like us doing GEFI right off the bat. So, so we're gonna kind of like work through this. This is also going to help us do our logistics regression. If you notice, if you look at these linear combination predictions, these can be larger than 1 and less than 0. So what happens is once we do the logistics regression, we're going to do this link formula so that things asymptotically approach 0, and then they curve up and they asymptotically approach 1. So all of our values are going to be between 0 and 1. But that's further on down the road. So, so we're choosing not to do this function. We could have done that. One of the limitations on the linus function is that it's limited to 64 features. However, in our model here, we could have done this. We have 20. Each one of these items are a feature plus the intercept. So we had a total of 20 items here if we look up at our linear model here. So if you just kind of drag across, and you look at the count down here below, you'll see 20. So we could have done this. Another alternate method we could have done was median regression. This actually minimizes the sum of the absolute value of errors. So we just did the sum of errors versus the absolute values of the errors. So one of the good things about median regression is if you have things that are like outliers, they affect it less. So that's one of the good things on that. All right, so just a little background there. So let's go on to slide 14. So if we look at, again, if we look at column W, this looks pretty reasonable. So if you look at the people that are pregnant, overall they have higher numbers. So let's just do this. Take your cursor and just grab from like W8 down to where you no longer see the ones, which are the pregnant folks. If you do this, what'd you guys get for an average? What'd you get for an average? So I have 0.73. What do you guys get?
0.73.
You have 0.73 too, George?
0.72.
Brian, what'd you get? Okay. What'd you get, Ryan?
0.72.
0.72?
I got 0.72.
Okay, so roughly 0.72 to 0.73. Okay. Let's look at the next columns that aren't pregnant. What would you expect? Would those values be higher or lower? Those values should be lower, right? So good. So let's go grab this and pull it down to the bottom here. Okay, so I got for pregnant, I got 0.72 to 0.73. For not pregnant, it looks like I have 0.27. What everybody else have? 0.27. So you can see, so there's like almost like a 0.5 difference between these. So this is what we'd expect our model to do. The more pregnant a person is, the higher their score is going to be, and then the average of non-pregnant is going to be lower. Okay, so this is what we want our model to do. So we'd kind of say that, looking at this, we would say, yeah, this is pretty reasonable, but let's actually do some concrete tests to go test this. So we're going to look at 3 different items. One of the things we're going to look at is R squared. This is going to be how well it fits the model, how well it fits that linear line. And then we're going to look at F tests. This is just going to be the probability that this just randomly fit itself together. And then the other key thing is this item called a T test. So we're going to look at each item, each coefficient, and see how much it drove it. And if we do that, even though we have like 19 features right now, perhaps after we do this, we're like, there's only like really 6 that matter. So let's go throw out everything else. We can just use the 6. Okay, so that's what this is going to kind of help us do. All right, so the t-test, I'm warning you guys, it's pretty funky. It's like doing all these like matrices and all these cool things, and the inverse of the matrix is pretty nutty, crazy math. But luckily, Excel's doing it for us. All right, so let's go into X2 in our formula, our sheet here. Okay, so you just hit Control and go up to the top. And then in X2, we want to do the total sum of squares. So this is kind of cool. We can use this formula here. But if we look at this, since our values are between 0 and 1, we expect the average is going to be 0.5. And if we square that, it's 0.25. And if you multiply it by 1,000, that's going to be 250. So spoiler alert. But let's just see if the math works here. So in X2, we're going to grab this formula. We're going to throw that up in here. Okay, so we get 250 like we did, like we predicted. Again, this is just the sum of if you look at the average, if you have 500 ones and 500 zeros, the average is going to be what? Well, the average is going to be 0.5. Okay, so if you have 500 ones and 500 zeros, that average is going to be 0.5. And if you take the difference between 1 minus 0.5 and then square that, 0.5 squared is going to be 0.25. So either way, it's going to be 0.25. And if you add up 1,000 0.25s, you're going to get 250. All right. So the next thing we want to do is the explained sum of squares. So what this is going to be is our total sum of squares is 250, and then we're going to take our error, 135 is what I had, and that's going to give us our explained sum of squares. So we're just going to say equals x2 minus x1, or you can copy over the formula, either way. Okay, so our total sum of squares is 250, and then if we look, our squared error is 135, so that 114, that's what we actually predicted out of that 250. The other 135 is just errors based on the fit here. If you had a super horrible fit, it would be 0, or actually we'll get to that here in a second, in the squared, R squared. So let's take the value of x3 divided by x2. So we're going to say equals x3 divided by x2. Okay, so I have like 45%, 0.457. So if this was perfect, our R squared would be our sum of, if we had a perfect model, our sum squared error would be what? What do you guys think? Would you want your error? So the total sum of squares is 250. If our model was perfect, what would our errors be? What do you guys think? 0, good. Brian, you're all of this. Okay, so it would be 0. Therefore, our explained sum of squares would be what? 250 minus 0, that would be what? 250. and 250 divided by 250 would be 1. Okay? So if our squared error was 0, we'd have a perfect model. If our squared error was 250, then it would be 250 minus 250, that would be 0, and our explained sum of squares would be 0, and our r squared would be 0. So that means our model would be garbage. Okay? So 1 is great. So you want your r squared to be the higher the better. So the closer it is to 1, the better your model is. All right? Questions here? All right, cool. All right, so let's go on to slide 16. Okay, and then this is kind of what I explained. 1 if the model is great, 0 if it's not great. So, and this only works if you're finding linear relationships in data. If you have a funky curve or something parabolic, like a U or V shape, it's not going to work. Okay, so little pitfalls there. So let's now go in. So let's look at the F test. What this is going to do is this is going to say, what's the chance that all these numbers got filled out randomly? So this is basically a test of how well the solver worked. If it's like, if it was like totally random, we'd say our solver isn't good, and then the lower the number is, the better our solver did at solving this for probability. So in Z1, what we want to do is we want to get our observed count. Okay, so this is just going to be our number of observations. So if we look at V8 down to V1007, that's going to be 1,000, but you can just scrape the formula and throw it in there. Okay, so that's 1,000. And then our model coefficient, this is going to be the count of our features. So this is going to be all of our coefficients plus the intercept. So this will wind up being 20. We have 19 features plus the intercept. So we'll put that in Z2. Okay, so we have 20. And then in Z3, our degrees of freedom are going to be the observation count minus the number of model coefficients. So this is just going to be all the different ways that this formula can kind of go, and there's going to be 980 degrees of freedom. So we're simply going to say equals Z1 minus Z2. We have 980. So this next formula is a bit funky. This next formula calculates the F statistic. So, and then we're going to actually go in and put it in the probability value of that. So this is going to be x3 divided by x1. So our degrees of freedom divided by the observation, the ratio of that, times the ratio of the freedoms or degrees of freedom, and then the model coefficient minus 1 to take out the intercept. So let's just scrape this one and throw this in Z4. Okay, so you guys should have come up with like 45, 43, somewhere in there. Anybody not get that? Everybody's there? 42.5, somewhere around 42, 43, 44. Anybody get anything different than that?
41.7.
Yeah, sure. I'll take that. Or actually, no, it should be, everybody should have the same. So let's see, let's validate. So you guys have 1,000, and then 20, and then 980. Okay? And then you just scrape this formula, and then you copy that into Z4. We should all pretty much have the same, right?
Isn't the sum squared error different?
Oh, I'm sorry. Yes, thank you, George. Thank you. Yeah, so this is going to be the x1 and x2. Yes, thank you. It's a ratio of the sum squares. I was thinking it was the observation count. So this is going to be the ratio of the sum of squares divided by the sum of squared error, and then times the ratio of the degrees of freedom divided by the mile coefficient 20 minus 1, which takes out the intercept. So, okay, yeah, so if everybody has between like 42, 43, 44, that should be good. Okay? The next thing we want to do is we're going to do this f-test p-value. So this is going to be the probability of chance that our model just got, you know, that solver just like threw everything into the coefficients on the 2 row to get our linear combinations. So just copy this formula. And we're going to put this in Z5. And it should be like some super duper low number. Okay, so what did you guys get?
20, what is 115?
Okay, so what does that mean? Like, so this is like, yeah, that number times 10 to the minus 115. So it's like, you know, 0.115 zeros and then a number. So probably pretty low probability that this just happened by chance. So we can say that, all right, solver worked and it actually solved this and it's not by chance. I would take those odds any time to Vegas or put, you know, money in Vegas and that all the time. You're going to win, right? Okay. So the first one said, here's the reasonability of our formula. And this is the probability that it just by chance grabbed those coefficients. So that's what this test is saying. So the next one we're going to work on is the coefficient t-tests. So we're going to start looking at which of these variables, which of those features are significant and which are not. So essentially the t-test assumes that our garbage, or that our model was garbage, and then we kind of proved to ourselves that no, actually it really was good. So this is going to be the same thing. This is going to assume that all the values are worthless, and we're going to pick out which ones kind of drove the pregnancy in here. And we're going to do all kind of funky things to get this. So in X5, we're going to get the prediction standard error. And this is going to be the square root of X1 divided by Z3. So what this is going to be, this is the standard deviation. This is going to be the standard deviation if you kept on basically grabbing 1,000 customers at a time. The probability that you're going to get different values in here, so like a 37% chance. Okay, so it kind of like it's definitely so it varies, and that's kind of why all of our values varied. We had a 37% chance of, you know, we did this 5 times here. We had a 37% chance of our values being different, is what this is basically saying. Okay. All right. So moving on. Okay. So the next thing we want to do now is go into the coefficient t-test. So let's go unhide our model coefficient standard error sheet. So we're going to right click, then unhide. And we have our model coefficient standard error sheet. All right, so I kind of filled this in for us instead of having you guys go fill it out here. So the first step we're going to do is we're going to take all the numbers and we're going to multiply them by themselves. So we're taking like this matrix. So you're taking a matrix like in columns, and then you're going to basically flip it into rows, and then you're going to multiply it by itself. So you're multiplying, like, you know, these, like, all these items from B2 to over to U2 and or over to U21 and rows times the columns, and you get kind of like this funky thing right here. So this is going to be this array, but you actually have to do it. You actually have to select the cells, then put it in, and then do the Control-Shift-Enter. So it's a little bit funkier than what we're used to. So grab B2 down to U21. And once you have this highlighted, what you're going to do is you're going to scrape this formula over here, over in Excel or over in PowerPoint. You're going to throw it in the formula bar. And you're going to go Control-Shift-Enter. Then that's what the that's what the matrix does when you take all the rows and then you flip them on the columns and multiply them by themselves. So anybody remember, like in algebra, doing like the matrices or whatever, like the matrix? So yeah, it's like those things hurt your head. So yeah. So what we've just computed here is we just calculated the sum of squares and cross products matrix. Okay, say that 5 times fast. Sum of squares and cross product matrix. Okay, so doing this, and to do that, we use this, M multiple. Then we did the transpose. So we took the linear model times the linear model, and we basically just crossed those over and came up with this model right here. So the next thing we want to do is for us to get the coefficient standard error calculation, we're actually going to take now the inverse of all this stuff, and then we're going to put that into B25 to U44. So just like before, you're going to come down and highlight B25 down to U44. Okay, and then you're going to scrape this formula over in PowerPoint. We're going to put this into the formula bar, and you're going to do Control-Shift-Enter, and that now gives us the inverse.
There was like a parenthesis indicated.
Did you guys get errors?
No.
Let me see. I don't think it had my values. Let me Control Z. Let's see, B25 to U44. Okay. Would it work for all you guys?
Yeah.
Let's see, what am I doing wrong here? Calculating B25. All right. Oh, I think I might have calculated too far over. There it goes. All right, so B25 over to U44. All right, so there we go. And let me see, let me pause for a sec here. All right, so now let me go back down into, all right, there we go right there. All right, cool. So now I'm back in business. All right, so everybody has this, it's all filled out, everybody's good. So yeah, it's pretty funky. We took all those things, multiplied them, and then we took the inverse of all those guys. So this is like kind of like funky, crazy, weird math. So this is like one of those do the I believes on. All right, so the next thing we want to do then is we want to calculate the diagonal of this. So to calculate the standard coefficient error, we're going to get all the numbers that's across this diagonal in the min inverse that we just did. So if we look at this in B47, we're going to have the formula. We're going to take the linear model X5, so that's going to be the probability of standard error in here, the prediction of standard error, and then we're going to multiply that by the square root of the index of the model coefficients, B25 to B44, times the, or finding the index of those values, B25 to B44, based on the B46 cell. So what this is doing is it's basically saying, hey, go in here, and it's going to use this index, and it's going to find the index of 1, and it's going to basically take 1, 1 right here, male, and then it's going to multiply that by the x5 value in the linear model. And then it's going to do 2, 2, and then 3, 3. So it's basically just going to go down that diagonal, but we actually had to do the transpose and the multiplication and then the inverse to be able to get the diagonal now. So it's basically going to take the diagonal of each one of those guys and multiply it by the x5 times the diagonal value, and then that's going to give us our values in here. So in B47, we're going to grab this formula. Okay, and I get 0.041166, so you guys should probably have somewhere close to that, similar. And you're just going to autofill that across over to 20. And now we have all of our different coefficient values that we can now take over into the previous chart that we had. So this is kind of like a scratch sheet work pad that we needed to do to go over and compute the coefficients in the linear model. So how's everybody doing? Everybody's good here? Everybody not good? Rock on, you guys are getting good at this. So then how do you guys feel you're like, you know, as you start seeing like all these like relative references, are you guys starting to get the hang of it and seeing it and seeing what's happening? And so if anything, you guys are Excel gurus after this class. All right, so the next thing we want to do is you're going to copy these values from B47 over to U47. We're going to copy, and then we're going to go back into the linear model. And we're going to come over here to row 3, and you're going to paste values. Paste values. So you can right click, and you just click that 1, 2, 3, and then that puts in our values right there. Okay. Coolio. All right, so then the next thing we can do is we can calculate the t statistic in row 4. This is going to be the absolute value of the model coefficient divided by the coefficient standard error. So it's going to take that and it's going to grab the absolute value. So scrape this formula right here. The absolute value of our coefficient divided by the coefficient standard error. Okay, and then you can autofill this across. All right, cool. And then now we're essentially going to do the t-test p-value on this to figure out which ones of these guys are going to be by random. So on this one, the lower, so anything that's greater than 0.05 in this case, we're going to say is essentially invalid. Okay, so just like the t-test model before, we said the lower the number, the better it was not by chance. So on all these guys, the higher the number, the more likely they're not a valid predictor. So we could kind of dump them out. So let's grab this t-test value in here. And then we're going to put that in B5. Okay, and we're going to pull this across. Okay. And you can see we have some, so these really low numbers are all good. And what are they? Stop, at the end, I have like stop buying wine times 10 to the minus 7. Bought wine, 0.08. Maternity clothes times 10 to the minus 11. So again, the lower the numbers, the better these guys are. So let's conditionally format these so that anything that's greater than 0.05 is going to show up nice and green, and those will be the values that, per our models, aren't really that good of features for us to use. So let's come into here to home. We can do conditional formatting, and you're going to highlight cells that are greater than 0.05, and let's just do we'll do the green, keep the green fill with green dark text. All right, so for me, so yours will all be different, but for me, it looks like male, female, home, and apartment weren't that big of factors for me. What did you guys have? You had the same? Anybody else have anything different?
Body pillow.
I'm sorry?
Body pillow.
Body pillow. So if you think about that, I mean, anybody can buy a body pillow. Maybe somebody's like arthritic or something like that. What did you have, George?
Same male, female, home and apartment.
Alex?
Same as George.
Same as George. Okay, so we all kind of had this. If you look across, so okay, cool. All right, so we're kind of all fairly consistent. So if you're doing data analytics, you could probably say, all right, we don't care about these, throw those out, and now we're just going to analyze all these other items in here, is what this is telling us. Because all these other, so all those other ones that are super low, it's like, all right, it's the probability of this just being some random value is really low. Okay? Questions, thoughts, everybody's good? Cool, all right, let's continue forward on here. All right, so now that we have our model, what we can do is we can actually go apply this to our test set. So if we looked at our test model, we had 50-50, but once we get into our model here, we're actually going to have 6% pregnant and 94% that aren't pregnant. So our test set data is going to reflect real life, however, we oversampled to build our model. So, and what we're doing here is we're basically running customers through, so we have a whole different set of numbers. So if your target, you basically you make your prediction models, and then you get your 1,000, and then you create your model, and then you grab a whole nother new set of 1,000, and you make it realistic based on 6% pregnant and 94% that aren't pregnant to make it a realistic sampling of likelihood. Okay? So on slide 24, we're going to run our test set data through our model in column B, like we did for the linear model, using the coefficients. So what we're going to do is, if you look at test set, so if you go into test set here, we have all these models over, so we have all these numbers over here. If you scroll down, you'll see that the ones stop at 61, plus the header row was 60, and we have 940. So what we're going to do is we're going to analyze these values, but we're going to use the coefficients that we came up with in our model. Does that make sense? So we're calculating these values, however, we're using these values for our coefficients based on the model that we created. And that's why we call this supervised, because we created the model, and now we're going to use that model to go actually run a test set of data through. Okay? All right, so in test set, let's go into V2, and we're going to do just like before. We're going to, here. All right, so what we're going to do is that same sum product value, but let's look at what we're doing this time. We're using the linear model, B2 to T2, those coefficients, and then we're going to multiply them sum product by the values in our test set. Does everybody see that? So if we look at our formula, we're doing a sum product of the coefficients from the linear model, so B2 to T2. Now notice we didn't go to U2 because we're just going to do the coefficients, and we're going to add the coefficient to the end, or the intercept to the end. So what we're basically doing now is we're taking like the mx of all these values, and then we're just going to add the b, which is the intercept derivative. So does that make sense? So we take all of these values up here, times each row here to get our linear prediction. And then once we get that, we just simply add on the intercept, is what we're doing here. So let's scrape this formula and throw this into V2. Okay, and I have 0.58. I'm just going to fill this down. Okay, so then now here's our values based on our test data. Oh, I didn't get it all the way to the top there. Let's see. Let me come up here and do it. So don't do like me, make sure you get it up at the top. 0.58. Okay, there we go. So these numbers look higher. So let's do our average again. Find the average. Oh, I still am off. All right, third time's a charm here. All right, here we go. And then I'm going to fill it down. All right, so let's find the average of all the ones versus all the zeros. So let me grab this. So I'm going to grab all my ones. So on my ones, I have an average of 0.75. So here's our test data, 0.75. What did you guys come up with? 0.71. Brian? Alex?
0.73.
0.73?
0.72.
0.72. So roughly 0.72. All right, cool. All right, so now let's go take the average of the zeros. So let's just grab our cursor and go down to the bottom here. Okay, and then that average for me is 0.27. So we kind of held, so if we look at this, our model kind of held through, which is pretty cool. Our model predicted almost with the same predictive powers or with the same result of the model. So that's pretty cool. So now we could say, hey, this model is pretty darn good. We took these 500 and 500, we trained our model. So if you're a Target now, you could take any 1,000, just go slam it in here. Or you could take 10,000 and slam them in here. It doesn't matter. So if you had 10,000 people you wanted to look at, instead of 60 and 940, you take 600 and 9,400. But the model should be the same.
Does it have to be like an even number? Like, does it have to end on 0, or can it end like on random?
It can end on a random one. You just want to have like 6%. In your test sets, you want to have like 6% pregnant and 94% not pregnant. But it doesn't matter the model. You do 500, 5,000, whatever. So that's kind of cool. All right, so let's keep going on. This is like cool stuff, man. I think I'm just too geeky. All right, so just like before, the model identifies households that are pregnant with predictions that are closer to 1. So the highest prediction values are for households that bought clearly, products that are related to pregnancy. So we just kind of already did this, looking at the non-pregnant versus pregnants. So one of the things we're going to start looking at now are the 4 types of classifications for data. And we're going to build this receiver operator curve. So this receiver operator curve is something that they created back in World War II to fight the war. It's based on radar returns, so you can better go fight enemies and use radar to go target items. And we're going to use that same concept here actually in our model. So if we look at the 4 different classifications that we have labeling. So true positives, this is going to be labeling a pregnant customer as pregnant. And then we're going to have our true negatives. This is going to be labeling a not pregnant person as not pregnant. And then we have our false positives. These are also type 1 errors. This is labeling a not pregnant as pregnant. And then false negative is labeling somebody that's pregnant as not pregnant. So between these, if you're target, would you rather have, just looking at false positives and false negatives, would you rather have more false positives or more false negatives if you're target? And why? You want to have more false positives, right? So what does that mean? A false positive means well, you're not pregnant, but we gave you a coupon. But it's like, maybe you know somebody you're going to give it to. What about a false negative? What does that mean? They're missing their chance. Brian, you're all over this. Seriously, you guys. I'm so excited for you guys. You guys are like this is cool stuff. I mean, did you guys even think or imagine, like, when you started this class, you'd be like, ripping through this stuff like this? I mean, this is pretty insane. I mean, I'm pretty impressed. So let's go take a look at all these guys. And like you guys, like the class was saying, you'd rather have false positives versus false negatives. False positive means, hey, you tag somebody as pregnant, that maybe wasn't pregnant. Maybe they'll give the coupon to somebody pregnant, or they'll use it to buy a present for somebody that was pregnant. So their likelihood of buying the product is probably far less than somebody that really is pregnant. So if you miss somebody that is pregnant, then yeah,
so it's kind of like it's better safe than sorry type thing.
Exactly. So you'd rather have more false positives than more false negatives, and we're going to see that they're kind of tied. All four of these guys are tied to each other in a measurement called precision. So the more precision you have, the more all these numbers start dying off. So the less it is, the more sloppier it is, then it's kind of tight. But we'll see this in a second here. So let's go unhide the performance curve. So we're going to unhide performance. All right. So we want to copy this formula in. And what this is going to do is it's going to find the minimum value that we have for somebody that's pregnant. And we're going to find a maximum value, and then we're going to set a range that flow, and then we're going to just fill in a series, and then we're going to calculate all four of those values over there. So in A2, you're simply going to grab this formula here. So we're going to find our minimum and test sets. So we're looking in that column of predictions. And I have minus 0.34. You guys will probably have something similar to that. Okay. And then A5, let's go find a maximum and throw that in over there. Okay, and I have 1.26. Okay, is that pretty similar to what you guys have? All right, cool. All right, so what we're going to do now is we're going to start with our lowest value, and we're going to fill a series in until we get to our maximum value. But we're going to set the minimum value in V2 to an increment of 0.05 that's actually less than that number. So if you look at 0.34, what's something that's an increment of 0.05 that's less than 0.35 or 0.34? Less. So not 0.3, go the other way. In between 0.3 and 0.4. 0.35, right? So let's start off with negative 0.35 here. So we're going to say negative 0.35. And this is based on my numbers. You guys do it based on your numbers. So what was your lowest number, Ryan? So negative, okay, so you're good. So you just see negative 3.5, Brian? Okay, so you'd start off with 0.35, Alex?
Negative 0.33.
Okay, so you'll start off with 0.35, George?
Negative 0.3.
Okay, so you'll start off with negative 0.35. And then does anybody, so several of you guys took 120, anybody remember how to fill a series? Anybody remember how to fill a series? So in the Home tab, if you go over into the editing group, you're going to see like this little drop down arrow thingy right here. It's going to say fill, click that arrow, the little right arrow, and you're going to fill a series. And then we want to do a row or a column. What do you guys think? We're actually going to fill this down. So we want to do the probability. So we're going to set up all the probability cutoffs. So we're actually going to want to do a column here. And we're going to do linear growth. And then what do we want to have for our step size? What do you guys think? So we're going to go from 0.035 or 0.35 to what? 0.3 to 0.25. So how big is our step going to be? 0.05, good. So in step value, where it says 1, you're going to put 0.05. And then we want to stop at a value that's 0.05 beyond our max prediction. So I have 1.26, so I'm going to stop at 1.3. Okay? So you'll have to adjust that based on your data. Then I'll click OK, and then we're going to autofill this guy down. And then you can click on column B, and you can just go in here to General, and you just make that into a number. You'll get nice, sweet numbers like that. Okay, everybody has that? So, like I said, you can format column B to just be number with 2 places. So how's everybody doing? Good? Everybody's there? Awesome. You guys are rock stars. All right, cool. All right, so, and then what we want to do now is we want to adjust the bottom one here, like where it says, mine says 1.3. I'm going to make this to that value, my max value over there. Because if you go higher, you're going to get a divide by 0. So I'm going to change mine to 1.26. Whatever your max value is, that's what you're going to put in here for this last value. And yours might vary depending on your numbers. So did everybody get that? So whatever your max value is, you're going to put that in.
What do we put for this series again?
You're going to put 0.05 as a step, and you're going to end at an increment of 0.05 beyond your max prediction. You get it, George?
So my max prediction was 1.25.
Okay, so then you just leave at 1.25. So you're going to say you're going to start at the low one, and you're going to say step value 0.05 up till you get to 1.25. If that's the case, you don't have to tweak the end. So then everybody has this last value set up to.
I have a really off value.
So we're going to take these cutoffs now, and we're going to figure out the precision, the specificity, the false positive, and the true positive rate. So the precision, this is going to be the number of persons that we've identified as pregnant who are pregnant. The true negative rate is going to be the specificity. True negative rate is going to be the number of pregnant that really are not pregnant. And then we have the false positive rate. That's going to be the not pregnant we said are pregnant. And then we're going to have the false negative rate. That's going to be the persons that were pregnant that we said were not pregnant. And we're going to use these formulas right here. So over here, so let's go over this formula really quick. We're going to use this formula called count ifs. So count if is going to be basically a count with condition of an if. But if we do count ifs, it's going to be multiple count ifs. If we have the count ifs, it's going to be multiple count ifs together, if that makes sense. So what we're doing is we're looking at test set, and we're looking at the values in column V. And if those values are greater than B2 for this particular one, if it's greater than B2, and if the test set is saying it's pregnant, we're going to count those guys, and then we're going to count that by all of the test set values that are greater than B2. And doing that is going to give us our true positive or true pregnant that are pregnant. So let's scrape this formula. Put this in a precision. Okay, and then we're going to put this, and then we're going to fill this down. And as our cutoff values go up, so you can just format this as a number again if you like. So what does this tell us? What does this tell us? What's this value saying? So when our cutoff value is really low and sloppy, what does it mean?
Precision is low.
So it means our precision is pretty low. Okay, it means our precision is pretty low. So what this is saying is, as our classification goes up, then our probability of getting pregnant women that are pregnant are higher. if by chance your last value says divide by 0, then whatever your value is, let's say mine is like 1.26, just make it 1.25 and back it down 1/100th until you get the value. So if you do like 1.26 and go to 1.25 or 1.24, you'll eventually get the 1. So just keep working it back until you get there. You got it, Ryan?
Yeah.
Awesome. You got it, Alex?
Yeah.
Perfect. Okay, cool. So again, precision is going to be the number of pregnant women we correctly got right. So the number of pregnant women that really are pregnant. Okay. The specificity true negative rate, this is going to be the number of pregnant that aren't pregnant. So this time, instead of doing greater than B2, we're looking at what the model had as less than B2, so basically not pregnant, and then we're going to count that, and we're going to multiply that and count them if they really weren't not pregnant, and then we're going to divide that by the count if of all the non-pregnant persons. So let's scrape this formula. So essentially we're saying, hey, if this is less than 0.2 and they're not pregnant, divided by the total number of pregnant, then we got it right for the total number of not pregnant. Okay, and then autofill this guy down, and then you can just do number again. So you go from general into number. Okay, so what else does this tell us? Okay, so this says the higher the classification, the higher the probability cutoff. What happened over to getting the not pregnant people right? That got better too, okay? However, comma, this is IT, and there's always a cost, okay? Let's now look at the false positive rate. What this is going to be is this is simply going to be 1 minus the true negative rate over here, okay? So just, you're simply going to say equals 1 minus D2 and autofill that down. So what happened here? So as our precision got better, what happened to our false positive rate? So it kind of went off the chart bad, okay? So we kind of have this trade-off. The more precision you have, the more accurate you're going to get true positive or true pregnant and not pregnant, but you're also going to have a lot more false positives. And you're also going to have a lot more false to negatives as well, or true positive rates. So let's go in and go to slide 20 or 30, and let's scrape this formula. So this is going to be the, in the test set, the people that are greater than B2, that it's saying B2 divided by the total number of pregnants. All right, so we come over here.
I think the apostrophe marks are getting away.
Yeah, it's probably so. So yeah, so if you put this in, and then if you get the value thing, just go update those apostrophes into the, just update them. And then you'll also do the same thing to the double quotes as well. And I don't know why when you copy them over into PowerPoint, when I made the briefing, it changes them over. So Excel's looking for a specific type of format here. Okay, and I'm going to make that into a number. Then autofill down. All right. So just like before, the more precision you have, the worse off your true positive rate is. So while you get, as the cutoff rate goes up, you get more pregnants that are pregnant, you get more not pregnants that are not pregnant, but you also have more not pregnants that you classified as pregnant and more pregnants that you didn't classify as pregnant. So that's kind of like the trade-off here. So if we look at this analysis, what we're going to do is we're going to create this receiver operator characteristic curve. So what we're going to do is we're going to plot the false positives across the false negatives, and then that's going to give us this curve where we could start looking at the trade-offs between these two. So to do this, grab E1 down to your last number. So for me, that's row 35. Okay, so you're going to grab E1 down to whatever your last number is down here in the F column. And then in the quick analysis tool, you're going to go into charts. And then you can just do a scatter plot here. All right, and then I'm going to kill my PowerPoint for a sec just so we have more space. I'm going to blow this guy up here. All right, and I'm going to move this guy over here. All right, so what we want to do is we want to change the chart type. So come in here and change the chart type and go to scatter with smooth lines. So it'll be that third one over. Scatter with smooth lines. Okay, and it'll take our points out here. But if we look at this, because our values could be less than 1 or less than 0 and more than 1, our chart's kind of funky. It goes from 0 up to 120% or 0 to 1.2. So let's kind of tweak our curve here to clean it up. So the first thing we want to do is click on the vertical axis. You double click on this, and when you do, you're going to get the format axis pane over on the right hand side. Everybody get that? Okay, cool. So let's say the minimum is 0.0, and let's just say the maximum is 100%. We don't care beyond 100%. So change that 1.2 to a 1.0. And then the next thing we want to do down here is where it says numbers, number down at the bottom, click on that and change number into a percentage with 0 decimal places. Okay, so now we have 0 to 100%. And we're going to do the same thing now to the horizontal axis. So click on the horizontal axis. And you'll see format axis. And then if you come over here on the right-hand side, you'll see the axis options as 3 little bar thingies. And click open axis. And you can say that the minimum is going to be 0. And then the maximum is going to be 1.0. And then change the number to %. And then the decimal places to 0. All right. Then we can come up here into our title. And we can just call this rock curve if you want to. Receiver operator curve. Or receiver operator characteristics curve. And then let's go add some, let's add axis bars. So we know that the horizontal is going to be the false positive rate and the vertical is going to be the true positive rate. Let me make sure I didn't flip those guys. Yep. All right, so go back into access. So then with your rock curve showing, just click on the plus symbol and just go access titles and check the primary horizontal and the primary vertical. And then down here on this horizontal for this access title, you can say false positive rate. And hit escape, or I'm gonna click this guy. And then I like mine to be a little bit bigger. So you just click, so I'm even gonna make it bold. If you go into home and click bold, and just make that guy bigger so that way you can kind of see what it is. And I'll do the same thing over in the rock curve. I'll bold that guy and then pump it up a bit just so you can kind of see it. And then over on access title on the vertical here, now we could put the true positive rate. All right, and then I'm going to make that bold and then kick that size up as well. All right, so what is this curve telling us? So now we put on our data analytics hat. We have our curves. So your boss is like, okay, so what? So what is the so what here? So let's go take a look at the values. So I'm going to shrink this back down again. All right, and pull this over so we're doing a rock curve. All right, so as we talked about, the higher the cutoff, the more precise the model. But it also kind of messes up our false positive rates and our true positive rates. So if we look at this, this is kind of cool because we can come over here and we can say, so essentially what this is saying is that, I'm trying to squeeze it in, so that's, so I'm going to make these guys a little bit smaller. I'm going to wrap text just so it's easier for us to see wrap text. All right, so now we can kind of see everything right here. So what this is saying is if we look over here, we could say like our false positive rates and then our true positive rate. So if you look over here to the bottom, this is kind of what we really want to focus on, our false positive rates or true positive rates. So as your probability cutoff increases, you're going to be more precise, but you're also going to be sloppier on the false positive rates and the true positive rates. So if you come over here, you can see that with this model, you can have like a 77% chance of getting a person that's truly pregnant with a 10% false positive rate. So that's pretty cool. So if your target, like, hey, we're going to send, we know using this model, 77, I mean, we can look at the data and we can tell 77% of the households that are pregnant. That's insane.
Only 10%.
With only 10%. So they're going to say, all right, we're going to send out 77% of these households, and we know that of the 77%, 67% of these guys are really pregnant. 10% aren't, but we hope that if the 10% throws the coupons away, we don't care. If they didn't do this, how do you know who's pregnant, who's not pregnant? So as a store, these guys could run these cards and these models, and they could say, wow, we know 77% of the houses that are pregnant. So you can start sending coupons out to those guys, which is pretty insane, I think. And then look what happens as our precision goes up. You know, as our precision goes up, our true positive rate starts going down. But what happens as this true positive rate starts going up? What happens to our false positive rate? So at 88%, 58% of these are pregnant and 30% aren't. So you kind of look at that ratio right here. This is probably going to be, like right in here is going to be our sweet spot, probably like 78% and 12% that are false positives. So you can say that with 78% accuracy, we know pregnant people, and of that, 12% are going to be wrong. So we have like 66% of the households correct, which is pretty insane if you're targeting these people. This is the same thing that's happening when you start looking at ads. I mean, that's how these guys, if you look at something, or if you go shop like for a car or something like that, for the next like 3 months, what's going to pop up in your web browser? All these cars, because these guys are using all these analytics to start targeting people. Is what's happening. Pretty nuts and crazy stuff. All right, good. So this is a great stopping spot. Excellent, guys.